you're ready for the second lecture by Riccardo Sturani on gravitational waves. Please, Riccardo, go ahead.
It's, yeah. The tea is not only for the Brits. I mean, we have tea every day. Okay, so today I have a very optimistic program. I'm sure I won't be able to do all of this, but in case I can probably steal 15 minutes from the discussion session. Okay, yesterday I gave you the overview, the astrophysical overview. Okay, let me spend 30 seconds. Okay, we have galaxy everywhere. By the way, how far is the distance, the closest galaxy to us? How far is that? Ah, good, you see. Okay, and here is the Earth out of scale. We have the interferometer, and then we have the gravitational wave that arrives here with an amplitude which is the kinetic term of the source divided by the distance, roughly. And this is dimensionless, because energy has dimension of length, okay? And then it comes with two polarizations. The two polarizations are, okay, it's not like the electromagnetic field, the two polarizations are circulating, but the two polarizations are parameterized by the two vector orthogonal to the direction. And then here's the detector. The detector, I told you, there is this laser and there is a photon detector here. So this detector detects only one combination of the two polarization because it detects one intensity of light that is responsible to specific combination. So the output of the detector will be some combination of H plus S cross, and the coefficients are generically called plus and F cross. So in all literature you find these two functions. And how many parameters this thing depends on? Okay, in the modeling here, this is ultra simplified. No, this will depend on the two masses and the two spins. Of course, the two spins will also affect the dynamics. We'll see how the dynamics of the source will affect the shape of the waveform. Okay, we haven't seen this quantitatively, but this should be easy to swallow. No, I mean the masses, the astrophysical property of the source will depend on the waveform. So these are already 8 parameters. So you might have heard that the waveform that hit the detector eventually will depend on 15 parameters. Okay, where do the other 7 comes? Okay, you must add 4 parameters for the location in space-time of the source. So you must have the time of arrival, the distance, and then Ra and Dec. Ra and Dec is basically our longitude and latitude in the sky. So that's why how astronomers point to objects in the sky. So of course you need 4 coordinates to locate an event in space and time. Okay, that should be easy to remember. And then we get to 12. So 8 intrinsic parameters to describe the source that determine the dynamics. And so you get this. Of course, this kinetic term of the object will increase, no, as the system is approaching merger. So the system is losing energy. The total energy of the system is kinetic plus potential, so it's minus kinetic, no? Because for the virial row, the potential is minus twice the kinetic. So the kinetic energy is increasing, the potential energy is decreasing, but in modulus is increasing, is going down. So this is increasing, and the rate of increase depends on the astrophysical parameter. Okay, so these are the astrophysical parameters that determine the actual time behavior of this object. Then you have 4 parameters to locate the object in time and space, of course. When it's arriving, the distance, theta and phi. Of course, you don't want to use Cartesian coordinate in the universe, no? You want to use polar coordinate. So where are the 3 other parameters come from? Because I told you, I gave you the spoiler that we have to get to 15, 8 plus 4. The other 3 parameters basically inside the galaxy. So let me zoom out. The galaxy is tens to hundred of kiloparsec. Then I zoom out to kilometer scale, and I see the 2 black holes. So the 2 black holes will have a preferential frame. No? Suppose there is no spin, so they rotate in a plane. So there will be a natural axis associated to them, and then which will be different from the radiation frame, okay? Because the radiation frame determines how H plus and H cross are projected into the interferometer. But of course, this source frame has nothing to do with the radiation frame. I mean, the orientation of the binary is completely arbitrary with respect to the direction we are looking at that galaxy. Clear, no? So we look at the galaxy, and inside the galaxy, I mean, the galaxy, it appears as a dot for us, but the galaxy is kiloparsec big. And inside the galaxy, there is a binary. There are two black holes rotating in some reference. And so how do I pass from this reference to this reference? Well, I need 3 Euler angles. Of course, no? If I have 2 different frames, arbitrarily oriented, I need 3 angles to relate the 2. And so these are the 3 Euler angles that 8 plus 4 plus 3, we get the 15 usual parameters to completely determine the waveform as it's spit out by the detector. So the 3 Euler angles you usually find in literature parameterized in this way. Psi, iota, and phi. Of course, you can label them the way you want, but that's standard just to ease your search in the literature. Basically, usually iota is the angle between the angular momentum, so the perpendicular to the plane, and the traveling direction of the gravitational wave. Phi determines the orientation in the plane on the orbit, and psi determines orientation here in the plane perpendicular to n. This is just a parameterization of the Euler angles. And that's why usually this parameter pattern function usually are made to depend on Rhine deck, of course, because if you change the location in the sky where you're looking at, you will have a different projection on your detector, which is fixed. Psi is usually included here, you see, because since psi is the third Euler angle that makes a rotation around n, psi trivially mixes the 2 polarization. Psi is just a rotation of x and y. So a rotation of x and y will just trivially mix h plus and a cross with the cosinus of 2 psi. Okay? So psi is usually included as one of the angle on which the pattern function depends. I mean, all of this is heuristic. You find in the notes the actual derivation. I mean, the actual derivation will take half an hour, so that will basically prevent me from talking about other interesting stuff. But this is just to give you, I mean, probably most of you won't ever work in data analysis, but you might want to read a paper about gravitational wave detection, and I'm giving you a map to get an orientation, how to understand. 8 parameters intrinsic to the source, 4 parameters to locate the event in space and time, and 3 parameters that really depend on the specific source. For a generic gravitational wave, you don't have these 3 parameters. If you just see a gravitational wave and you don't know how to model it, well, you don't have the intrinsic parameter and you just have the location in time and space. But since we know how to model it, we know it's a binary, then we have the intrinsic parameter and we have these 3 geometric parameters, which are the Euler angle of going to this frame, to that frame, okay? And so these are the way to really fundamentally determine everything we see in the detector from everything that was happening there, okay? If you think that's really beautiful, no? You have a really microscopic understanding of the dynamics there, and you translate it into a very deterministic, very precise prediction of what is happening in the detector. You just need, I mean, all of these parameters will affect in various ways the waveform. So in principle, when you detect things, you can detect everything. In practice, there are lots of degeneracy, so some parameters will be degenerate with others, so some parameters will be able to be detected with much more precision than others, but you know, that's life. I mean, that's physics. Okay, so let's go back now to GR. So our starting point is really, I mean, it's not very original, and so we just linearize it. So forget. So the idea is that when you look at the gravitational wave here, close to the detector, you can forget any nonlinear things, okay? This object, as I told you, is 10 to the minus 20 instantaneously. So forget. Also, the output of the detector doesn't need to be linear in the 2 polarization. But of course, when this object is 10 to the minus 20, nobody will ever be so stubborn to go to second order, okay? Here, but not here. Close to the source is a completely different case. Close to the source, nonlinearities are important. And actually, it's predicting the gravitational wave, it's all about the nonlinearities at the source. So, but here, when we look here, we can forget nonlinearities, so we just linearize. Plus d mu, d alpha, h alpha nu. Well, let me put a symmetrization. I mean, a sloppy notation just for symmetrization of this object. It's a mu plus mu. Of course, this is symmetric, must be symmetric, just to spare chalk. Okay, and then what do you find in standard textbooks? You say, okay, I apply H bar. By definition, H bar is the trace reverse. Gravitational, H is the trace of the gravitational perturbation, H bar is the trace reverse. I mean, much like G mu is the trace reverse Ricci. Well, G in general. So G is the trace reverse Ricci, Ricci is the trace reverse G, H bar is the trace reverse. So basically, if you expand Ricci linear order, you obtain the same expression but without the bar. When you move from Ricci to Einstein, you basically put the bar and you're safe. A linear order, of course. Then we go to the, it's very, yeah, this is correct. Then you go to the Lorentz gauge. So we have a coordinate transformation. We know we can kill 4 components. It's convenient to do this. So we go to the Lorentz gauge. So we automatically get rid of this. And we're left with this. So you see, still, this is a linear equation, but it's still coupling different polarization. What we want to get at the end is to a simple equation that doesn't mix different polarization. And this we can do in the following way. We can use some residual I mean, this is the coordinate transformation for the bar H. No? If it was the coordinate transformation just for H, it would have been this. But for the bar the H, I get this extra piece. I mean, not much of a big deal. This is standard textbook stuff. What I want to emphasize here is that this condition, if I apply it, so if I have this condition equal to 0, then if I want the new object equal to 0, then I must have box. Okay. Yes. So this is a box. Box. Okay. So basically, what I can see is that, yes, this is. Yes. Basically, what happens here is that this is correct, right? Let me check. Yes. Yes. This is the transformation of H. If I want to do this, then I do d mu h mu plus d mu h mu plus, okay, d mu, okay, now it's correct. You see, these two objects cancel. And so basically, I'm after a coordinate transformation. I'm left again in the Lorentz condition, provided my psi, my arbitrary transformation, satisfies the box equation equal to 0. Satisfies the Lorentz equation. Then you may wonder, wait. We had 4 degrees of freedom in the coordinate transformation. We use them all, and still I have something left to kill some extra degrees of freedom. So at the end of the day, I kill 4 here, then I kill 4 more, and I'm left with 2. You see what I'm doing? This is standard textbook, and you find in all GR books. But I just want to go through it to understand what it means physically. Okay. So I'm basically killing 8 degrees of freedom, not 4. And basically, I can use this residual gauge transformation. I have my h nu. This is the 0, 0 component. This is the xx, yy, zz. So for instance, I can use psi 0 to kill h bar, to kill the trace. Then I used psi I to kill the H0i. I use psi I to kill the psi 0i. to kill the H0i. I use Xi0 to kill the A00, and then I left the Lorentz condition is just left to for instance, this, but this is equal to D0, A00, because I already killed. I use Xi0, and I use it to make, I use Xi to do H0i equal to 0. So I kill the trace, I kill this tree, I use this extra thing. Then the Lorentz condition on H00 means, tells me that this is not time dependent, so it cannot be a wave. So I put a 0 there. And then I have the other condition, d mu h mu I, which is equal to d0 a0i plus dk hki. This is already 0 because already killed. This is the divergence, but you know it's a wave. Let's consider a plane wave. It only depends on z, t minus z, say. And so in this way, I can also call all the z component, hiz, hxz, xyz, hxz, hyz. Why? Because if this object is only depends in t minus z, so this is only a derivative with respect to z that has to be 0, then it has to be constant. Then again, it's not a wave, okay? So if this derivative is with respect to x, it doesn't do anything, because h doesn't depend on x. If the derivative is with respect to y, it doesn't do anything. But if it's a derivative with respect to z, it tells me that h dot has to be 0. But a wave that doesn't depend on time is not a wave. So I kill this. Okay. So this object is traceless. And so I'm left with only 2 degrees of freedom. No? 4 I killed from the Lorentz condition, and 4 I killed from the extra condition. And so I'm left only with 2 degrees of freedom that are usually parameterized with h plus minus h plus, because the trace was already 0, and h cross. So, I mean, when I do this in the chair course, many of my students get confused. Let's hope to dissipate the confusion. So at the end of the day, I'm left with 2 degrees of freedom. What is happening here? Is gravity parameterizing, is gravity fully described by only 2 degrees of freedom? I mean, what about the Schwarzschild? You know? The Schwarzschild sits here, for instance, no? The metric perturbation to Schwarzschild, here there should be a minus 2m over r, you remember? And here I killed it. Why? It's not a wave, no? It's a static piece. So it's physical, it's there, it's responsible for many interesting effects, like the fact that I'm stuck to the floor, for instance, but it's not a wave. And what it means that I can kill with this extra degree of freedom, with this extra liberty, with the extra freedom that I have. It means that here, I'm killing, you see? What I do with h v nu, no? H v nu is changed by this object. And let's call this object Xi mu nu. So it's a symmetric to tensor that depends linearly on Xi. Basically, what I do, h v nu, I can add an object which is Xi mu nu that depends on these 4 Xi mu's. And what happens? In vacuum, I have to solve this equation, box h equal to 0. But since I can shift h v nu by xi mu nu, which also satisfies box xi mu nu equal to 0, well, it means that h mu nu, the 4 degrees that satisfies box equal to 0, are completely absorbable. Okay? These 4 extra degrees of freedom can kill completely 4 degrees of freedom that are inside h mu nu, provided that my equation is box h equal to 0. If my equation was box h equal to, like in Schwarzschild, like a delta r m, for instance, this degree of freedom cannot be killed by these x mu's. Okay? So these x mu's only kill longitudinal degrees of freedom, only kills degrees of freedom that are related to source and do not radiate. The degrees of freedom, these 2 degrees of freedom that survive this extra freedom are the real radiative degrees of freedom that survive in vacuum. Let's do the case of electromagnetism. Might be simpler. In electromagnetism, a mu has 4 components, okay? A0 and Ai. But we know that the photons have 2 polarizations, 2 radiative degrees of freedom, okay? So we have 4 degrees of freedom at the beginning, mathematically. We have 2 radiative degrees of freedom. What happens to the additional 2? One is taken away by the gauge freedom. Okay, electromagnetism has gauge freedom, but gauge freedom is 1 degree of freedom, is lambda, no? A mu goes into a mu, then the mu is lambda. Where is the other one? Okay, we have 2 radiative, 1 gauge, there is still 1 to give 4. Well, it's the Coulomb degrees of freedom. No? In electromagnetism, you have Coulomb attraction, repulsion, you have magnetic forces. Those are responsible, are physical. I mean, Coulombic attraction is physical. It's just not radiative, okay? Because those, the electric field goes as 1 over r square. And the Poynting vector goes as e square. So e square for the Coulombic field goes as 1 over r fourth. Is not radiative, no? If you measure it over succeeding sphere, it goes down. It's not radiative. It's not taking away energy. So there you have the longitudinal degrees of freedom, the Coulombic degrees of freedom, that is mediating force between objects, but it's not radiative. And so you can kill it in vacuum, but it's physical because it considers attraction and repulsion. In gravity, you have the same. You have 4, which are really gauge, which are really not physical, but 4 degrees of freedom that you can get rid of only in vacuum because they are the longitudinal degrees of freedom. They are the gravity analog of the Coulomb potential. Okay? So this gravity analog of the Coulomb potential, we don't want to see them now because we want to look at radiation. And radiation is really 2 radiative degrees of freedom. But those 4 longitudinal degrees of freedom will be ultra important, for instance, to determine the dynamics of the binary. Okay? Of course, because here you have the relativistic gravity, and you have to take into account all possible interaction of this longitudinal mode. Okay? So this distinction is often overlooked in books, but is actually at the basis of phenomenology. Gravity, like electromagnetism, you see, phenomenologically, gravity and electromagnetism have very many things in common, whereas from the fundamental point of view, gravity has many more things in common with QCD, like the title of this conference says. Okay, but phenomenologically, what do you have? You have 2 kinds of phenomena which are very distinct. So the Earth is going around the sun, so clearly there is some gravitational force. I mean, it's very physical and very important for all what we know. But that's the longitudinal mode, okay? Earth is not radiating. I mean, the gravitational wave emitted by the Earth solar system are very weak. So what happens to the Earth? As it goes around the sun, the momentum changes a lot, the momentum, by changing direction, okay? The energy of the Earth basically doesn't change. So what happens when the Earth goes around the sun? There is a continuous change of gravitational mode, but this gravitational mode has 0 energy and a lot of momentum, okay? So these gravitational modes are off-shell or longitudinal or potential modes, okay? So we have a lot of potential modes that make the Earth go around the sun, but they have virtually no radiative modes emitted by the Earth-Sun system. Here, when we look at the binaries, that's where the things get interesting, because we have a lot of potential modes being exchanged between the 2 black holes that make the orbit, you know, going not straight, but in orbit, actually. And you have also radiative modes that are escaping from the binaries and hitting our detector, okay? So the 2 phenomena are very important, but phenomenological are very distinct. But also theoretical very distinct, because one phenomenon is associated to K, that is omega n, okay? This is the radiative mode. And the gravitational mode that are exchanged between these 2 black holes will be of the type virtually, not exactly 0, but 0-ish, and some strong space momentum, okay? So this is at the base of, when you treat this system, it's, I mean, of course, you could treat everything in covariant theory and plug everything inside, and, you know, the theory would give the right answer if you're good enough to do the computation. But at the computational level, it's much easier to split the 2 sectors. To split the sector where you have most exchange of potential modes, and the sector in which you have most exchange of radiative modes. Basically, leakage of, not really exchange, but leakage of radiative mode. So this is the basis of what you might have heard of near and far region in the gravity literature. So in the near region, what is important is the exchange of off-shell mode, and far zone, where you have the exchange of radiation modes. Okay, this is the gravitational literature. In theoretical, in particle physics literature, these are called potential modes and radiative modes. So near region, far zone, near zone, far zone, potential and radiative mode separation. And now we'll look at an example of this separation, and to how that will help us in reproducing with very simple computation the Newtonian potential. And you might say, okay, just the Newtonian potential. Maybe we don't need all this machinery to compute the Newtonian potential, right? But this machinery smoothly extends to all other orders, which of course I won't do today, but you find the sketch in my notes. Okay, so I hope I gave you this very clear basic point. So you have exchange of potential modes and leakage of radiative modes. The two effects are very important, but very distinct qualitatively. Of course, it's the same underlying theory, GR described both, but we want to treat them separately because they give rise to a very distinct phenomenology. Okay, now let's go back to the quadruple formula I derived yesterday, because I want to give you some more hint about it. Actually, so you remember, no? So we start with this. I won't write G anymore. Okay, we have this. Now we have to solve, but just for the radiative mode. So it's convenient to go to the TT gauge, transverse traceless gauge. And so the solution of this is H bar Ij. So I immediately drop these two space-based component equal to minus 16 pi Tij divided by box. 1 over box, I mean, it's just the inverse, it's just the green function. No? The inverse of the D'Alembert is the green function. Okay, this is not quite right, because these are still 6 components. Here are 2. So what I have to do is this. Ij, KL, KL, where this lambda is the projector. PJL plus I. There is probably 1/2 PIL, PJK minus PIJ, PKL. What is P? Well, P is the analog projector, but for electromagnetism. No? For electromagnetism, if you do this construction for electromagnetism and you want to pick up only the radiative degrees of freedom, you take the 4-dimensional, you kill time by gauge choice, and out of the 3 space component, you kill 1, you kill the longitudinal one with this projector. Again, this projector is just to single out the radiative piece. There is also another piece, which is not radiative, which is physical, but we just not interested in it right now. Okay, so this is the electromagnetic projector, and the G gravitational wave projector is sort of square of it, sort of. Okay, so the lambda only appears in front as a prefactor, so we don't have to care about it anymore. So the box is minus 1 over 4 pi, d3x, x minus x prime, tkl retarded time. Okay, I think I wrote it all. Okay, I just explicitly wrote the box. So we simplify what we need to simplify. The lambda stays in front. So this, I did the trick yesterday. This we can trade it by repeatedly using the conservation of energy momentum tensor into two derivative of the quadruple, which is basically the kinetic energy of the system. But now I want to draw your attention to something else. So the source is here. At kilometer, the source size is kilometer, and we are 100 of megaparsec away. 100 of megaparsec, kilometer. And we bring it out, and we call it D. Okay? This is brutal approximation, but I mean, come on, we are allowed to do that, no? Kilometer against 100 megaparsec. By the way, you know, when you do electrostatic multiple expansion, you just expand over modulus x prime divided by modulus x, and then you obtain first moment, second moment of the source, third moment of the source, you obtain dipole, quadruple, and so on. That's the static multiple expansion. We don't want to do that. We want to do the radiative multiple expansion. So this is just approximated by the distance, and it's constant. Basically, we are saying that the source is a point. We don't consider that the different points of the source are a different distance from us, here in the denominator. But look at here in the numerator. Here in the numerator, yes, we do want to consider, because different points of the source are emitting in different time. Because, you see, the observer is sitting at some time t, and it's one time of the observer. So the wave arrived at one time, but the wave that arrived at one time will receive coherent contribution of different points of the source at different time. To arrive at the same time, the point of the source that is closest to us has to meet later, and the point of the source that is farther from us has to meet earlier. And you might say, well, this is small. Well, this is small, but not negligible. Prime, and so this will become let's not use the conservation of energy momentum tensor. Let's keep it as TKL. So this is T minus R plus. Okay, I expanded this to first order. No, this is just this is square root of x squared plus x prime squared minus 2 x, x prime. Okay, this is just the modulus, is just this. And then if you expand to the first order, you obtain this. You obtain R, sorry, I call it D. You call it D minus unit vector in the direction of D dot x prime. Okay, why I cannot neglect? I mean, and then of course higher order, which I forget. The higher order I forget because there will be size of the source divided by the distance to the source with respect to this. But this is basically an offset. This is retarded time. Okay, this is retarded time, and it's an offset. This object is actually different, okay, when I integrate it here in different point of the source. So let's expand it. So there is this prefactor that I just don't copy. It's the same. And then I have here D3 x prime. Then it's TKL T retarded x prime. And then I have plus T dot. This is the time entry. Time dot in the same point. N dot x prime plus T double dot divided by 2. Okay, you know. I don't need to remind you what a Taylor expansion is. Okay? So, for this expansion to make sense, we need that the first order is smaller than the previous order. Okay? So, what is the small parameter that allows me to go from here to here? So, you see, n is dimensionless, it's just the unit vector in the direction of the source from the Earth. X prime is the vector that runs around the source. So, basically, the size of x prime is, say, L, the size of the source. But here we have a time derivative of t, so this is basically omega, the frequency of oscillation of the source, no? Time derivative, so 1 over time omega, okay? So this is the small parameter, I mean small parameter, we have to check if it's small, but this is the parameter that allows me to go from leading order to the first order. Is it really small? Well, yes. This is the frequency of the motion times the size of the source. This is the velocity, the internal velocity of the source. As long as it's smaller than 1, then we can do expand, okay? So this is the multiple expansion. Why multiple? Because you see, here you get the time derivative of the source, the first moment of the source. Here you didn't write it, but you will get the second moment of the second derivative of the source, and so on. Okay? So the small parameter of the expansion is V. And basically, this is the post-Newtonian multipolar approximation. And so in the multipolar approximation, we can express the gravitational wave amplitude as an infinite series, starting with the second derivative of the quadruple. I derived it yesterday. And then first moment of Tij, second moment of Tij, and this will involve octupole, hexadecapole, and so on. And will also involve not only moment of the energy, but also moments of the angular momentum. So here you start with the quadruple. Here you have octupole, which is the third moment of the mass. And you also have magnetic quadrupole, which is the first moment of the angular momentum. Of course, energy and angular momentum do not radiate because they are conserved. Dipole do not radiate because the center of mass is conserved. So quadrupole, second moment of the mass radiates. Zero antisymmetric moment of the momentum doesn't radiate because it's the angular momentum. But first moment of the angular momentum does radiate, and it comes from here. So you find the details in the notes or in any textbook. But this is just to tell you this is the quadrupole, electric, or the mass quadrupole. Here you have mass octupole and angular momentum quadrupole, so the first moment of the angular momentum. And here you will have hexadecapole of the mass, so first moment of the mass, and second moment, how do you write a second moment? Second moment of the angular momentum, and so on. Okay, so this is the multiple expansion. And you have a factor of V every time you go from one to the other. So how does this relate to the energy which is emitted? Well, this we have to go back to the Einstein equation and allow for second order. Any question on this? Okay, I need to do some space. So here, let me rewrite the Einstein equation in this way. Let's do the trace reversal on the right-hand side. So I do the trace reversal on the Einstein equation, so I write them back as as a function of the Ricci, and then I put the Ricci second order. So what happens here? This is the first order, it's waves, no? It's waves. This is the second order. The second order will involve some h square. So what is crucial here that while this is oscillating, this piece has a part which is not oscillating, no? Because you get a cosinus, you multiply by cosinus, you get a cosinus square. Cosinus square will have a piece oscillating with twice the frequency and a piece which is constant. So basically, when you average over some time, this is not zero. When you average over some time, this is zero, because it's linear in the perturbation. This is not. So it makes sense to bring it on the other side and to consider it as an emphatic contribution to the, I mean, in this form, it's an emphatic contribution to the trace reverse energy momentum tensor. Okay. And so at the end of the day, we can associate an energy momentum tensor to gravitational wave, which is basically this. Okay, there are a few caveats in this formula. So the mu, so if you ever try to expand the Ricci to second order, there are many more pieces than this, okay? But it collapses to this when you go to the TT gauge. But the TT gauge is correct if you are only looking to radiative pieces. And the radiative pieces are the only one that carry away energy. The longitudinal mode do not carry away energy of the system. So we're justified. And, okay. And then if you translate it into H plus and H cross, then basically you get that this is H plus dot square plus H cross dot square. And there are the brackets. The brackets means that I'm averaging over a time which is longer than the period of the oscillation. And so at the end of the day, we get this very simple formula for tau 0, 0, for the energy density. Basically, each polarization, apart from the non-canonical normalization, basically each polarization is contributing as a single scalar field. You can treat the energy contribution of each polarization if it was a single scalar field with the appropriate normalization. Question? Yes. Yes, only the piece that is not averaged to zero over or integrate. I mean, here we're talking of frequency of 100 Hz, no? So you want to average over second, over whatever macroscopic scale. This is the part that survives. Yes, I mean, the equation you can consider instantaneously, right? You don't do the average. But this is just to get the interpretation of the energy carried away by gravitational wave. No? Whenever you have a wave, forget gravity, but whenever you have a wave, electromagnetic, even a mechanical wave, it doesn't make any sense to consider the energy. Just consider a wave in C. You have waves, and then you take a point, and you say, oh, I want to compute the energy of the wave in that point. Doesn't make any sense. You have always to average over at least a wavelength, actually more than a wavelength, okay? Otherwise, the energy is not conserved, because you look at a point, sometimes it's still, sometimes it's not. When it's still, it has zero energy. Yes, of course, the energy is moving away. It's moving around. Either you average over a size of your medium, which is larger than a wavelength, or it doesn't make any sense to give the energy of the waves. This works for mechanical waves, this works for electromagnetic waves, this works for gravity. So in this sense, there's nothing related to engage freedom of the observer. No, it's very fundamental thing about waves. Okay, and so we get. So now we plug this. We have the amplitude. We just have to go back and plug that formula, and we know how energy is carried away. Of course, the energy density is also the energy that goes away, no? Because tau 0. The two components are basically the same, no? Because suppose we have a plane wave or other wave, this dependence is t minus z or t minus r if it's a spherical wave. So the t00, the amplitude, the magnitude is the same as the momentum carried away by the wave. These are massless particles. Okay, so we apply this to the formula that we obtained, and we got the flux. Oh, I mean, luminosity is actually luminosity, the energy radiated per unit of time. So this is the energy density. This is the flux of energy, so the energy that crosses a unit of surface per unit of time. So what we have to do to get the luminosity, or the E in dt, you get to integrate over a surface. So the r square, we take it outside of this object. Okay? Of course, sorry, here I call it d, here I call it r. It's the same thing. Then, of course, the d square counts the 1 over d square from here. And of course, this tells you why we have all the right to forget whatever goes as 1 over d square here, 1 over d cube, and so on. Because when we insert it into the energy and we take the large d limit, it will go away. So the only part of the field that is really carrying away energy is the part that goes as 1 over d. Whatever goes as 1 over d square or higher, I mean, it's important. I mean, of course, the longitudinal mode do like this, no? The gravitational field is 1 over r square. But doesn't carry away energy. Because in the limit of large g, it goes to 0. So this is the only piece that carry away energy. This is the only piece we have to take care of. And so at the end of the day, we get to have the omega of lambda ijkl, qij qkl with the appropriate factor in front. Qij qkl, sorry, triple dot. Why? Because this is the zero moment of the energy momentum tensor. Yesterday I told you, that this we traded for the second moment of the quadruple. So this is a quadruple double dot. But the energy is h dot. So there is an additional dot. So Q3 dot, the r square goes away, the few factors there. And be careful, we have to integrate over all directions. Not all directions are the same, because in each direction the energy emitted is different. The amplitude of the wave depends on the direction. This depends on n, because this depends on n. Okay? So the integral over the direction is all on this lambda projector. Of course, this is about the source. The source doesn't know about the direction is in. The source is there. But the energy emission depends on n. And if you do this integral and you plug in the right number, then you get, if you plug in the right numbers, then you get the famous quadruple formula with the right numbers, which now I will tell you. Yes, which is basically G Q3 dot ij over 5. So the G, we could guess it, because we have here we have a G, of course, I usually work in the units G equal to 1, but this is just from the Einstein equation. Of course, the gravitational wave is proportional to G times the source. It's just the coupling. So where the G square has disappeared? Because with our interpretation of the second order Ricci as energy momentum tensor, since the energy momentum tensor has a G in front, the Ricci didn't, so the Ricci comes with the energy momentum tensor gravitational wave comes with the 1 over G. So the 1 over G kills one of the two, but it stays 1G. Okay, so this is L, the luminosity, is energy per unit of time, so it's dimensionless. Shall we check this is dimensional? Yes, because this is time derivative of kinetic energy square. Kinetic energy is dimension of length. Time derivative is dimensionless, so it's correct. So if we do, how does it depends on the property of the source? Well, this is m times r square divided by t cube, all of it square. Okay, this is the quadruple square. A quadruple is second moment of the mass, quadruple two derivative, and then an extra derivative because this is h dot. Of course, this is dimensionless. You realize now this is dimensional because mass is length. And so let me write this as ml L cube divided by t cube. So m over L by the Kepler's law is v square. M over r is v square. So this gives me a v to the fourth. This gives me a v to the 6, v to the So it gives me a v to the 3, that becomes a v to the 6. So overall, I get a v to the 10. So this is a famous quadrupole formula expressed in terms of the orbital things. And then one thing that is important is this is the symmetric mass ratio. Okay, there is the symmetric mass ratio square, because of course each quadrupole is reduced mass times length square. So here will appear reduced quadrupole square, reduced mass square. Reduced square, I write it as eta square times mass square. Okay, and then you find the right factor. And this is the result of the quadrupole formula expressed in terms of the orbital variable. So you see, at the end of the day, the mass do not enter, only the velocity, as it should be, because this object is dimensionless. The E in dt is dimensionless, okay? And so the mass cannot enter. Well, it can enter, but then also the radius of the orbit must enter, but then you can trade the two via the Kepler law, and you get this, okay? So now what I want to get, before going to the actual Feynman diagram computation, is the following. Is to use this emission, compare it to the energy of the system, to check how the rate or the life, basically, of this system. Questions? Okay, so basically, just those of you who have lost me, just bear with me the next, in this 30 seconds, I'll give you a summary. Basically, what do you have? We know that, we know this, no? We know that the amplitude of the waveform is just an expansion of multiples. So this is the quadrupole, second moment of the mass. This is the octupole, third moment of the mass. There is also the moment of the angular momentum, not only of the mass. Forget it. And so this is an expansion. So from going to this term, you pay a factor of V. This is what we learned. On the other end, we know that the luminosity at leading order goes as just Q3 dot square and nothing else, because this is dimensionless, this is dimensional. That's all what you need. This is what we learned. Now we have to compare with the energy reservoir of the system. No? If the system is emitting this, we have to check what is its energy reservoir and see how fast it drains energy. So the energy is minus 1/2 eta mv square. Circular orbit. Kinetic energy plus potential energy. Potential is minus twice the kinetic energy. The luminosity is, let me get the right number. Well, who cares? I won't get, let's forget the numbers now. Okay, this is the luminosity, not the angular momentum, luminosity. How do I get the lifetime of the system? Well, the E in dt is equal to, forget the numbers now, v dot, but at the same time must be equal to this. Okay, I equate the derivative of the energy, assuming that it stays in circular orbit, to the luminosity. The in dt is dimensionless, this is dimensionless, this is dimensionless. And so we get v dot is equal to eta v to the 9. Again, I forgot all the prefactors you find in any books or in my notes. And so this is easy to integrate. You get dv 1 over v dv in dt. It's eta v to the 8. Okay, so this is the logarithm of v, or if you like, the f, 1 over f, the f in dt is equal to 8f to the 8/3. You remember the Kepler's law under these guys, I told you yesterday, is the velocity is the frequency to 1/3. So velocity cube is the frequency, okay? So by forgetting the numerical factor, it's easy to translate a differential equation for V to a differential equation for F. Of course, there will be differing from a few numerical factors, but since I'm forgetting them from the beginning. Okay, and this we can integrate easily. So we get, sorry, there is an m that I forgot, of course. 1 over m, 1 over m. So the way integrated this, so F must be equal to, okay, but this is, wait, I need some help from my notes. I need some help. Okay, yes. Yes. Okay, so F, no, there is something wrong in here. So this, maybe it was too, yes, sorry. Yes, this is wrong. Sorry, I was too quick, sorry. So this is correct, okay? So this is just it's called energy balance equation. The derivative of E is equal to the leak of energy. So the dimensions are fine, 1 over length, 1 over length, and it goes as V to the 8. So you may, okay, one funny thing, no, somebody like me always like to think in terms of order of magnitude, relevant scale. Look at here. So here you might think, okay, V is dimensionless, V is dimension, it is dimension. The only scale that tells you that, I mean, we want to know what is the lifetime of the object. There is only one scale here, it's the mass. What is the mass in seconds? Microscopic. The mass of the sun in seconds is 10 to the minus 5 seconds. Then you say, oh, this thing should be very efficient in killing the object. Well, this is one case in which dimensional argument fails miserably. Because you say, okay, everything depends on m is the only dimension full scale, the time must be of order m. Wrong. Because it's of order m times a function of v. And v can be very small, can be 10 to the minus 3, 10 to the minus 4, can be to the high power. So it can get 10 to the minus 20 easily. And so the naive dimensional argument fails miserably. So let's change this with the frequency, because actually when we look from far away, we don't see the velocity of the binary black hole, but we see the frequency that is hitting on us. So that was I was doing wrong earlier. So this is the F in dt, 1 over F, that apart from the numerical factor is the same of this, no? Because V cube is linear in F, so when we take the logarithmic derivative, it's just a numerical factor. Here is n over V, but then we have to put the right m here, no? Okay, this is correct. Okay, so at the end of the day, we get F dot is equal to m chirp to the 5/3, F to the 11/3. What is m chirp? Well, m chirp is just m eta to the 3/5. I mean, I just define this m to include the symmetric mass ratio unit, just the definition. But it's very convenient that basically tells you that the mass parameter that determines how quick the system goes is m chirp, is not m. Okay? And that's natural, no? Because if one or two masses goes to 0, you would expect the lifetime has to go to infinity, no? Because it's always the light object which is emitting more. If one or two masses goes to 0, basically it's not emitting anything, and so the lifetime. So the mass chirp then goes to 0 and is not emitting anything. So about getting the lifetime. Well, we just check this. Well, you could tell it also from here. D in dt, you can say that D in dt is something like eta square eta times v to the 8 times v squared times m divided by m. Okay? So this is the energy, so this must be the inverse of time. D in dt is the flux which is emitted. I just take out, single out a factor which is the energy, so the rest must be the typical lifetime, inverse. Indeed, the typical lifetime is scales with m, but it scales with 1 over eta, and it scales with v to the 8. Okay? Sorry, v to the minus 8. That's important. Okay? And so this tells you, yes, what sets the scale is m, but first, it can blow up if eta goes to 0. And second, it blows up because v is never really 1. At most, it's 10 to the minus 2, I mean, for astrophysical systems. For the black hole of LIGO, this is really close to 0.1. But in general, for astrophysical systems that are standing there, can be, for instance, the double neutron star is 10 to the minus 3-ish. When it's 10 to the minus 3, here you get 10 to the minus 24. 10 to the plus 24. So you see, you easily go from microseconds to a macroscopic time. Basically, there is this factor. When we trade this as a function of frequency, let me write it up here. Then it's as a function of frequency m, and then it's mf to the minus 1/3. I just replace v as a function of frequency. So let me write it here. So the time is again m chirp f to the minus 5/3. So this is dimensionless. This is time f to the minus 1. Okay, so this is the typical lifetime of a binary system. True, the only dimension, if you use v, the only dimension full scale is m, but it can be increased by many order of magnitudes, depends on the velocity, the initial velocity. Or if you write in terms of f, then you have this combination which is dimensionless and 1 over f. So one way to remember is that the time should be inversely proportional to the mass ratio, as I explained. And so the power of the chirp mass is fixed to get 1 over eta, and then the remaining power of f is fixed by dimensional analysis. Okay, so this is the lifetime of a binary. So there are two things. First, it can easily surpass the age of the universe, though, because this is microsecond, but this can easily be 10 to the 30 or whatever. So the age of the universe, you know, it's 1 year is pi 10 to the 7 seconds, time 10 billion year, so it's pi 10 to the 17 seconds. Okay? This is the age of the universe. Pi 10 to the 17 seconds. This is 10 to the minus 5, 10 to the minus 6. This depends on v. So whenever you have a v which is smaller than 10 to the minus 3, here it becomes 10 to the 24, 10 to the 24, 10 to the minus 3, 10 to the 19, you're already out. You see? That's why here it's a relevant case where all the dimensional argument that I like so much to use fail miserably, that if you just consider the mass, you are missing some 20, 30 order of magnitude. Okay? So that tells you that either the system is now very, the system is relativistic to start with, or you don't see it merger within the age of the universe, point one. Point two, which is also very important, is that what is the time it's missing, it still have to go before the merger, depends very steeply on the initial frequency. This has a lot of impact phenomenologically. Because if you start seeing the merger at some frequency, or if you start seeing at a frequency which is twice smaller, then you have 8 times more time, almost, no? This minus 8 over 3 is almost 3, no? 2 to the 3 is 8. So if you build an instrument that is able to push back the lower frequency at which you observe the system by a factor of 2, then you have 8 times more time to observe it. You know, for astronomer, that's a game changer, no? So that's why for LIGO, you can see a neutron star for 1 minute. For ET, you can see for half an hour, because it's more than a factor of 2, okay? So for the third generation detector that will push down the low frequency limit of the noise, then you can really see an object merging for much longer time. And of course, it also matters the mass. No? The lower the mass, the longer it stays in band. No? Negative power. It's of course, no? Because the smaller the mass, the higher is the merger rate, the merger frequency. So the lower the mass at fixed frequency, the longer you will observe it, because you're observing a lower mass. Going back to the plot of yesterday, if this is your detector noise curve, so for LIGO, we are at 20 to the kilohertz. And the signal goes like this. And if you have a detector that can push back the lower frequency, then this part might not be large in frequency space, but corresponds to a large evolution in time. So you have much more time. Okay, and then one other thing that you might be wondering. So whenever people plot the spectrum of the gravitational wave, usually people plot a negative slope curve. Okay? So at high frequency, there is less power. At low frequency, there is more power. How come? I told you, no, that the gravitational wave amplitude is k divided by d. K is the kinetic energy, and k increases as you go closer to the merger. No? So for instance, we have a mass like a neutron star, so that the merger is here, a few kilohertz. So here, the instantaneous amplitude is larger than here. How come? And then in Fourier transform, people usually write this plot with a negative slope. You understand the apparent paradox. So at low frequency, the instantaneous amplitude is smaller. At high frequency, the instantaneous amplitude should be larger, but then when you look at the plot in Fourier transform, the slope is negative. This is a fact. You can open any plot in literature, the slope is always negative. But it doesn't fit with this intuition that the instantaneous amplitude increases. Well, you have to remember one thing, that the Fourier transform is an integration over time. So here, the system evolves very slowly. No? The time to measure here is large because the frequency is small. Here, the system evolves very fast. So here, there are many cycles that are contributing to this frequency bin. Here, there are few cycles that are contributing to this frequency bin. So despite here, the instantaneous amplitude is higher, but it's integrated over few cycles, effectively. Of course, you integrate over the whole history, but effectively, there are few cycles that contribute. I mean, here, there are many cycles that contribute to this frequency bin. Here, there are few cycles that contribute to this frequency bin. Let's do the thing quantitatively. Basically, the Fourier transform, you have to take v square of t e to the 2 pi f plus I phi of t integrating dt. Okay? So this is the kinetic energy is v squared. The mass, I put it outside. It doesn't change the frequency behavior. And I have to take the Fourier transform. So for the Fourier transform, I need to know the phase exactly. So let's do approximately. Let's use this thing that basically the Fourier transform at a frequency f receive mostly contribution only when the instantaneous phase is oscillating with that frequency f. Okay? So I say that this is v squared e to the pi f plus I phi of t star plus I phi dot of t star. Sorry, this is mine. I mean, anyway, the amplitude is oscillating with the cosinus, so there is plus I phi and minus I phi. And then there is plus I phi dot over 2 t star. The definition of t star is that phi dot of t star is equal to 2 pi f. F is my external variable, no? I want the Fourier transform at the frequency f. And then I say, look, the wave is oscillating. And whatever contributes to the frequency f is mostly the time chunk around the time where phi dot is instantaneously equal to f. That's a reasonable assumption. If I make this reasonable assumption, okay, here. Of course, you have when the wave is a cosinus, you have the two terms with the plus and minus. The one with the plus, you get it, you throw it away because it's wildly oscillating, and so the integral is 0. The piece with the minus, these things cancel, and so you see, sorry, here there is a t minus t star square. Of course, I'm doing the Taylor expansion, so this is t minus t star. The Fourier transform e to the 2 pi ft is the Fourier transform. So this cancel with that. Okay, t minus t star, the t star goes away, it's a constant. So this cancel to that because of the condition I imposed. And so I'm left with the constant, and then left with the Gaussian integral. Okay? So this is what is called a stationary phase approximation. And the result of this Gaussian integral is easy. Again, if I forget all the numerical factor, it's easy to get. It's just the v square in front, I consider is fixed. This is the v square at t star times the Gaussian integral, and the Gaussian integral okay? This is the Gaussian integral. I'm integrating over t, the result of the Gaussian integral. So this is 1 over sigma, basically, of the Gaussian. It gives me this. Okay, dimensions are right because this is a Fourier transform. It has to have dimension of time. So there was an m over d that I didn't carry around because they are constant, and anyway they are dimensionless. So this is dimensionless. Integrating over time must have dimension of time. Indeed, it's dimension of time, no? Definite double dot. But this is the same thing as v square divided by f dot to the 1/2. Phi double dot is f dot. Ah, f dot, our old friend. Did I count? Ah, yes, it's here. So, surprise, surprise, we get f to the 2/3 from here, and f dot to the 1/2 minus 11/6, which is equal to, again, proportional, which is equal to 4 minus 7/6. Okay? So the slope of h tilde is minus 7/6, and that's a definite prediction. Okay? That's unescapable prediction of GR. Okay? So now, in the last 20 minutes, unless you have questions, I want to go close to the binary and see what happens here. So how do I describe in the post-Newtonian approximation the dynamics here? Shall I? Okay, you have time until I raise things to ask me questions. Okay, remember, this is h tilde, but remember I told you yesterday that the signal-to-noise ratio square is the integral or the f of h tilde square divided by the spectral noise density. These two have different dimension because there is an integral in the f, and this is dimensionless. So we'd better, if you want to plot something, I mean, apple-to-apple comparison, you better plot this against that. So if here you plot the ASD, the amplitude spectral density, which is the square root of Sn, you better plot on the top of it square root of f times h tilde, which have, of course, square root of f times h tilde will have a different slope than minus 7/6. You just do the math, okay? Just for you to know how to compare theory to experiment. So now let's go to this formula. I can write with the factor right since it's easy. There is a 4 integral from 0 to infinity. Okay, now let's go to the near region. So you have time until I raise everything for questions. Yes. When, sorry? Yes, yes, this doesn't depend on eta. It's just that it takes forever to merge, but it's actually... No, it just grows very large, but it's physical. I mean, well, in the massless case, in this, well, you have the quadruple is you have to redefine properly the quadruple. The quadruple formula doesn't carry over easily to the quadruple, no? Because my quadruple is reduced mass times x. So if you define properly this, but then you know you don't have, you have to check if you have circular orbit. I mean, this applies to this definition of the quadruple or to circular orbits. If you have a massless object, then you have to be careful if these two conditions holds. No, for either remote, that carries over without any caveat. It just takes forever to measure, but that's physical. It does take forever to measure. And it's actually, the post-Newtonian is more and more accurate. Okay, the post-Newtonian dynamics is more and more accurate in the sense that if you start with small velocity, it will take forever to get higher velocity. So a small velocity approximation will always be correct. What is not going to be accurate, that you might find in literature that post-Newtonian waveforms are not accurate for LISA, where you have a high mass ratio. Where is the problem lies there? Lies on the fact that those waveforms, they have some inaccuracies just in the way they are integrated. And if you have a zillion of cycles, like basically you have as many cycles and you can accommodate in your observation time, the small error that you're making in the beginning, it just adds up all the way. So that's the problem. But the problem is that when you build up the waveform and that you have a small error. But yes. Okay, now, I didn't tell you the momentum, I only told you the energy, but just take the other component of the energy momentum tensor I wrote. Multiple expansion I did, near a far zone. The H bar where it disappears, maybe I get to that. Taylor F2 waveform is what I just did. So this I already did, this I did, this I did. Now I do this, maybe I will tell you where all the H bar disappears, but you won't understand this question if I don't do this first. So basically what we want to do is to consider the dynamics of two black holes. In fifth-year language, of course, you're all theorists, and then you can easily compute this diagram. So this is a black hole, and this is a black hole, but it's a point particle, so we don't care it's a black hole. It could be an electron. Well, actually, we want to be scalar because we want to complicate things now. And then it exchange a gravitational mode. So this model a black hole, just a point particle with a word line. This is the action of the point particle minus mass d tau, if you like. No? Just the integral over the word line. And of course, we have the bulk action, which is 1 over 13. No, this is 16 pi g. 4x square root of g gauge fixing. Okay, so we have the standard Einstein-Hilbert action plus gauge fixing. No, we want gauge fixing because otherwise we don't know how to invert the equation of motion for the gravitational mode, and we don't know how to write Green function. No? So I told you that already the equation of motion in this gauge fixing is very simple. It's h mu nu equal to 1 over box 8 pi g t mu nu. So basically, there is a tensor structure here, but it's simple. It's mu alpha eta nu beta plus eta mu beta eta nu alpha minus eta alpha beta eta mu nu t alpha beta. I mean, there is a tensor structure which is just a prefactor, so you won't complicate the computation. That's the good of this. That's the good thing of the harmonic condition. And then you just have to write the Green function, the appropriate Green function for the box. Okay? Actually, the box, this is constant, doesn't apply there. It applies only here. Of course, in Fourier transform, it's easier, it's just algebraic. And so we just have to apply a source. It's feeding the other source through the gravitational mode it has emitted. And how does it know? Quantitatively through the Green function. So the effective potential, or the effective action, there will be basically d tau 1, d tau 2. Then there will be m1, m2. And then there will be a Green function of t1 minus t2, x1 minus x2, where x1 depends on t1 and x2 depends on t2. Okay? And that's it. Basically, I'm assuming that this object contains I just open up the proper time, which is the word line action. The proper time, as we all know, is g mu nu dt square minus, well, depends where you put the signal. So g mu nu dt square plus gij dxi dxj. There is also, of course, the mixed term g0i dt dxi. All of this is inside the square root. This is the square root that defines the proper time. I mean, Nothing fancy. And then you develop the square root, and then you start to obtain first order interaction, like with H00 with no power of velocity. Okay? So the first order interaction is very easy. It's basically dt1, dt2. So the dt1 interacts with the H00, the dt2 interacts with the H00. What is the H00, the first particle? Well, it's the H00 emitted by the other particle. It's basically the green functions times the other particle source, and vice versa. Particle 2 interacts with the gravitational mode of the first particle, and so the particle 2 feels m1 times the green function. No? That's probably it's boring stuff for you. Okay, why I am dwelling so much on it? Well, because I want to show you something. Let's write the, oh, first this is much easier to write in Fourier space, so let's write it as d omega over 2 pi d3k over 2 pi cube. And then I have k square minus omega square plus some sort of I epsilon, which I don't really care about, I will tell you in a second. And then I have the exponential of the Fourier transform. Minus I2 e to the minus plus I k x1 of t1 minus x2 of t2. Okay, so this is quite boring. No? I mean, I guess you must have seen this many times. So why am I doing it? Well, because I want to show you what it means going to the near zone in this kind of problems. So we know that this is the potential. No? At the end of the day, this must give us the Newtonian potential. But it's not quite trivial how to get the Newtonian potential. I mean, if you want to do the full integral here, it's not so easy for such a simple process. What happens here that we have to remember what system we are looking at. We are looking at a system which is rotating around each other. So in the near zone, it's not emitting much. So this is the distance L, whereas the frequency of the emitted is omega, which is V over L, right? Because the frequency emitted is 1 over T, the period of the system. The period of the system is much larger than L, okay? Period is L over V, where L is the size of the system, okay? So clearly the frequency is a much lower scale than. So basically, these two black holes are exchanging a lot of potential mode, which have k, spatial k, 1 over L, way before you can start seeing the emission of radiation, which has frequency L over V, okay? So here there is frequency, which is of the type V over L, which is 1 over T, 1 over T, and then there are potential mode, which is basically 0, 1 over L. This is much harder than this, okay? And so let's do the following. Let's implement that this is much harder than this. Let me skip this piece that from now on will be a spectator. Okay, let me write it. Let me skip the 2 pi's. Okay, forgive me. And also the d3k, I write it down here. Then I do e minus omega blah blah blah, e to the ik blah blah blah, and then I write k square 1 plus omega square divided by k square plus omega 4 divided by k fourth, and so on. Okay, you see, I'm implementing mathematically what I know happens physically. So physically, this is a fact. I mean, we know that the Earth is going around for billions of years and is not emitting anything. Okay, so I know that the potential modes are much stronger than the radiation mode. And then if I do this, well, this integral becomes much easier. The integral in omega becomes just a delta in omega. And look at here. M1, M2, dt1, dt2, and then I get e to the minus omega t1, 2. And then, sorry, I do the first integral. This gives me a delta of t1 minus t2. There's no omega. I do the second one. It gives me dt1, dt2, delta of t1 minus t2, and so on, times the exponential. Okay, the exponential in omega, I already took it away with the integration. I'm left only with the integral in k. X1, t1 minus, opa. It's okay? So the integral in omega, I've done it, and it gives me out deltas times some time derivatives because I have. So you see, this approximation allows me to put omega in the numerator, and omega in the numerator is traded for a derivative with respect to times. So there is a nice physical interpretation of this. You see, by saying that radiative modes are softer than potential modes, I'm expanding over delays. You see? I'm saying that the interaction between the... Now this is not a Feynman diagram, these are two word lines. Basically, relativistically, I know the particle 1 feeds particle 2 at some earlier time, and particle 2 feeds particle 1 at some earlier time, of course. But this approximation tells me that the potential, I can compute it instantaneously. Equal times, equal times, equal times. Provided I add correction for the trajectory. Makes sense. The position of the particle here is fully determined by the position of the particle here plus derivative of the trajectory. With all the derivative of the trajectory, I would be able to reconstruct the entire trajectory. So you see what the approximation is doing? Is allowing me to reconstruct the total trajectory by approximating with the instantaneous interaction. So the Newtonian approximation is just the instantaneous interaction of GR. What is the error I'm making? Higher derivatives of the trajectory. So if I just do the math, here I get M1, M2. So for the first term, I get dt1 e to the chi, now is x1 of one time minus x2 of the same time divided by k squared, integral in d3k. Of course, integral in d3k, 1 over k squared gives me 1 over r, the Newtonian potential. What is the following term? Well, the exponential is the same. Then I get dt1, dt2. We get k v1, k v2, k to the fourth, times the same exponential, because I have the two derivatives, no? One derivative brings me down k v1, the other derivative brings me down k v2. But then I have k to the fourth, so this gives me 1 over r. This gives me v1, v2, divided by r. Again, no? 1, 2, 5k, k to the fourth, so it's still 1 over r, but it's v1, v2, and so on. So you see, I'm expanding over delays. Okay? And I get correction v squared, v fourth, and so on. So, yes. Yes, because in GR, I know that this, okay, this is the Feynman diagram. This is the Feynman prescription. What I should do is I should write the potential for particle 1 with the retarded propagator plus the potential for particle 2 with the retarded propagator of particle 1. So what happens is a property that G Feynman is equal to 1/2 G advanced plus G retarded, plus another piece that doesn't matter here. Mathematically, this is true, provided that you write the proper piece here that is 0 in this case. And so, at the end of the day, it's convenient just to write down the Feynman propagator, even though it's not physically motivated. GR is a causal theory, no? So particle 1 feeds the particle 2 through a retarded propagator, and particle 1 feeds particle 1, I mean, with the other retarded propagator. It happens that the sum of the two gives the Feynman, apart from a piece that I don't have time to enter now. So here I write the Feynman prescription, but it doesn't really matter, because what I'm saying that this never go on shell. That's the full point. I'm computing the contribution of diagram that never go on shell, so after all, this doesn't really matter. And never going on shell allows me, basically, this was the effect of retardation that was written here in the retarded and advanced propagator, is at the end traded with the knowledge of the trajectory to all derivatives. No? This particle depends on the trajectory of the other particle here. This is not what is written here. The potential depends on the other particle at the same time. There are corrections for the particle trajectory. So all this infinite correction of particle trajectory reconstruct the trajectory, and if you sum them all, reconstruct the causal theory. So I obtain an instantaneous Newtonian theory plus correction, and the correction, of course, instantaneous theory cannot be exact fundamentally, but is exact approximately. And the other correction, all the infinite correction, guarantee that my theory is consistent, because at the end of the day, it came from a causal theory. Okay? And so we have all these corrections. So at the end of the day, you remember, for H, we have Q, double dot, octuple, triple dot, and we are going in power of V. Here we get powers of V's square. So it's only powers of V's that matters in my post-Newtonian theory. But there is one caveat. At the end of the day, look at this. I'm integrating over all omegas and over all k's. In the domain of integration, I've written nowhere that omega must be smaller than k. I mean, I put it by hand. I mean, I did this expansion. I'm guaranteed that this expansion recovers this only when omega is smaller than k. But this is not what is written here. I'm integrating all omegas and all k's. So this equality is a huge cheat. This equality doesn't hold if I keep the integration over a whole domain. But there is a theorem that allows me, that guarantees that this is not a cheat. I mean, formally, it is a cheat, but it works. It works for, okay, I have, let me write down in 30 seconds. That cheat is actually justified, and it's called method of regions. So if people argue, oh, but here you are expanding, then you are integrated over, here integrating omega going to infinity and integrating for k going to 0. For sure, omega is not smaller than k in all of the region of integration. But there is a theorem that allows me that says me, and it's the theorem that tells you that the method of region works. And how to save it is, I want to check the notes because I want to do it very quickly. Okay, where is that? Okay, let me do, I'm sure it's in the notes, but let me do very quickly on the memory then. Oh, yes, I found it. Okay. The theorem tells you that, look, this is a cheat, but this is a fix. What is the fix? It's the following. 1 minute, I will give you. So, you know, this result is so nice and so physically, you know, stringent that it would be a pity to discard it just for some mathematical approximation, you know. Mathematical approximation should be at the service of physics. Physics doesn't need to respect mathematics when it gets to the right answer, right? Oops, I hope people don't quote me on this. So, and what is the, you know, the result is so beautiful that it must be right. And people find out the way to justify it. And the way to justify it is the following. So, this is an approximate interaction, what we are writing down. No? The real interaction between the two particles should be this. You write the full propagator and the Fourier transform in full detail. What I'm doing here, I'm doing a near zone approximation, which is this. Of course, this cannot reproduce all of this. I mean, it's an approximation. So what I'm saying is that I'm doing an error, but I'm not doing a mistake. No, it's not wrong. It's just that I'm doing something not very precise. And the fix is the following. I add the far zone. The far zone is this. Oh, k squared minus m squared. Okay? So the far zone is this. Oh, where did this come from? Well, I take the full theory. The full theory should integrate exactly this. But this is usually too complicated to do. Well, actually, people might disagree on that. But it's complicated for me, at least. And I say, OK, what I did so far was this. And I say, oh, look, then the theory came to rescue me. Look, if you add this piece to this piece, then you're fine. Instead of computing the potential in the full theory, compute it in the near zone and compute it in the far zone, and you're fine. Why this is considered far zone? Well, because here I keep the entire propagator, and here for the sources, instead of the full exponential, I consider moment of the sources. No? When I integrate over the sources, this is source 1, source 2 mass. This is source 1, x1, source 2, x2, source 1, x1, x2, source 1, x1, x1, source 2, x2, x2. So this is the multipolar expansion under disguise. Here, expanding the exponential like this means that I consider my sources as multipolar expansion of the sources. Dipole, quadrupole, and so on, but with the full propagator. Here in the near zone, I consider the full exponential, but with retardation expansion. Here, retardation exact, multipolar. Here, point particle, no multiples, but retardation expansion. And the theorem says that the sum of these two is equal to the full theory. And so I broken the original difficult problem into 2 sub-problems. Each of 2 is much easier. And the theorem goes like this. That I mean, the theorem takes 20 pages, but I do a very sketchy demonstration of why you can even think that, I mean, if you look at this, you say, oh, it must be crazy to say that this plus this is equal to that. No, it's not crazy, because it's the following that happens. So I say that the integral of this over all case is equal to the integral of the far plus the integral over the near over all case plus the rest, plus integral of small for k large. So let's say plus and what I mean for k small or k large, so k larger or smaller than a certain k bar. So as long as there is a separation of scale, I can cut the k integral to some k bar, here larger than k bar, here smaller than k bar. So the sum of these 2 reconstruct the integration over all k's. And here I have I minus n minus f plus n plus n, so this is a trivial identity. Okay? You agree with me that this is a trivial identity. Now I'm fine if I demonstrate that this is 0. And this is 0, I'm fine. Okay? And now this is easily done. Because look at this. When k is large, I'm in the near zone approximation. So even in the far zone, I can, so this approximation is good. I is n, so these 2 cancel. And f is 0, because you see, I'm in the k large. So I can approximate this like that, and then I have only monomials of k. And in dimensional regularization, what does it do in monomial of k? 0. When I go to k small, in k small, this is right. So k is smaller than r. So this is right, I can do it. So I cancel f. And n is 0 for the same reason as before, because n, it was already expanding here, but now k is small, I can also expand it here. I get only monomials of k. This is 0 in regular dimension, in dimensional regularization. So I demonstrated the theorem in my 5 extra minutes. And so the cheat I did here is not actually a cheat, it's just a partial answer. So this is correct, provided I eventually add the far zone. The far zone is basically treating the 2 particles as 1 blob, but with mass, angular momentum, quadruple, octuple, and all that, interacted with all sorts of gravitational modes. Provided that I add the 2, I get the full theory back. Okay, sorry for the extra time.
Okay, so since we're slightly over time, I suggest we postpone the questions to the discussion session, or you can just ask Riccardo during the coffee break. And we might...
I have an answer where h bar disappeared, because when you do Feynman diagram, there are all sorts of h bars.
You can do it during the discussion session. Yeah. And let's reconvene at 11:05. Okay.